Now that we've defined our equilibrium criteria and talked about stability, we're now going to use our knowledge about equilibrium in order to help us to understand phase transformations of pure substances. So for the cases where we just have only a single chemical species. Okay? And so, to be precise, when we talk about phase transformations or phase transition, it's when we observe a discontinuous change in the properties of a substance. In the properties of a substance, even when you just change its environment infinitesimally. Changed only infinitesimally. Okay? And so some common examples would be, if we're talking about water, when you boil water, it goes from a liquid to a vapor. Or you melt ice, where you see that as soon as you hit 0 degrees Celsius, that ice, it doesn't warm up anymore. It first just all melts, and then it will continue to warm up. Okay? All right. And when we talk about, when we observe these discontinuous changes in properties, and so that we get different forms of a single chemical substance, we call these different forms phases. Okay? To help us study, the phase behavior of different chemical species as a function of, a lot of different variables, what we could do is we could plot the different phases of a substance as a function of these variables. And when we do that, and when we visualize this, we call that a phase diagram. Okay? All right, and so one example that you've already seen before is the phase diagram of carbon dioxide, where the y-axis here is pressure, the x-axis is temperature. And you see that in this phase diagram, there's a lot of different features here. In each of these little panes, you see labels for, what phase the carbon dioxide is. In this region, it's a solid. In this region, you have liquid carbon dioxide. And in this region, you have a vapor. These dark lines signify what we call the coexistence curves. This is where you have two phases, or this is where the carbon dioxide will transition from one phase to another. And so if you were at a temperature of minus 56.6 or near it, and a pressure of somewhere between 9.9 and 72.9, you would see that if you went this way, your carbon dioxide would turn from a solid to a liquid. It would melt. And if you went from here to here, you would see that your carbon dioxide would evaporate from a liquid to a vapor. Okay? And then if you're directly on the line, you could exist as both a liquid or vapor. Or over here, you could be a solid and a liquid. And over here, you could be all three, solid, liquid, and vapor. Another feature that we haven't talked so much about yet is something called a critical point. What that means is that if you're at a high enough temperature, so if you're above 31 degrees Celsius for carbon dioxide, what you see is that the carbon dioxide then exists solely as a gas. And even if you increase the pressure of it, you'll see that it never turns into a liquid again. All right? So we'll talk more about that later. But in any case, you've seen phase diagrams before. You've seen them since, I expect, Gen Chem 1. But here in this thermodynamics course, we're going to rediscuss them and re-explore them in the context of equilibrium. And so all the equilibrium criteria we talked about in the previous videos, we're going to apply that towards understanding how chemical substances transition from one phase to another and what makes them stable in each of those phases. Okay? So we're going to use our criteria to help us not only understand the phase behavior of different chemicals, but because we're going to do it in a rigorous manner and we're going to develop mathematical models, we'll also be able to just predict the phase behavior of any chemical species that we want.